Welcome all to the problem solving session of the thermodynamics course from NPTEL. I am Pradeev E. I am one of the TA for this course. Today I have some problems on steady flow energy equation concepts, and then we will move on to the problems based on the second law of thermodynamics using heat engines, heat pump and refrigeration. So moving on to the problem, the first problem is shown on the figure, shown on the slide. Air flows steadily in a pipe at 300 kilopascal, 77 degrees Celsius and 25 meter per second at a rate of 18 kilogram per minute. Determine the diameter of the pipe, rate of flow energy, rate of energy transport by mass. Also determine the error involved in part C if kinetic energy is neglected. So I am drawing the system. We are given air flowing to a steady pipe, flowing steadily in a pipe. So air flows at 300 kilopascal, 77 degrees Celsius, which is 77 plus 273 Kelvin. So which is 350 Kelvin. The velocity of the flow is 25 meter per second, and the mass flow rate is 18 kilogram per minute. So we can, to calculate the diameter of the pipe, we have the mass flow equation given by m dot is equal to rho AV. Rho is the density of the medium, A is the area of the flow, and V is the velocity. So for this we can calculate rho using the equation of state, PV equal to MRT. So rho can be written as P by RT. So here P is 300 kilopascal, which is 300 into 10 power 3 pascals, and R is 287 for air, and then temperature is 350 Kelvin. So rho can be calculated. So rho is 2.986 kg per meter cube. So in this equation, m dot equal to rho AV, we have m dot value given as 18 kilogram per minute. So it is 18 by 60 kilogram per second. So I write down the values. 18 by 60 is m dot, rho is 2.986, and since it is a pipe, it should be circular, so the cross section area is given by pi by 4 d square, and we have to find the diameter for the first part of the problem, and velocity is 25 meter per second. So diameter is 18 into 4 divided by 60 into 2.986 pi into 25 under root. So this can be calculated. So this is 0.0715 meters. So this is 71.5 mm. The next part of the problem is to calculate the flow energy and the rate of energy transport by mass. So I will calculate the total energy that is transport. Total energy is m dot into half V enthalpy plus half V square, which is V square by 2. So here we know so here H is equal to Cp into T. Cp value we know that it is 1005 joule per kg Kelvin for air. M dot is 18 by 60, and H is Cp into T, which is 1005 into 350. and for the kinetic energy we have v square by 2. V square is 25 square by 2. So this way we can calculate the total energy. So this is those 105.62 into 10 power 3 joules, which is 105.62 kilojoules. So this is m dot is in kg per second, so this will be in joules per second, or it can also be written as 105.62 kilowatt. So now so this forms the third part of the problem C, and for the B we are supposed to calculate only the flow energy. So flow energy is m dot into h, which is 18 by 60 into 1005 into 350. So this is 105.52 into 10 power 3 watts, or it is 105.52 kilowatts. So in flow energy we have neglected the kinetic energy. Now the next one is to calculate the total energy neglecting the kinetic energy. So that is neglecting kinetic energy. Total energy is m dot into h. So h plus v square by 2 we had, and now we make this v as 0, so we have only m dot into h. So this is again the flow energy that we have calculated, which is 105.52 kilowatts. Now we are supposed to calculate the percentage error in calculating the total energy in this way. So the actual total energy is including v square by 2 we had 105.62 minus the flow energy neglecting kinetic energy, phi 2 divided by 105.62 into 100. So this was this is 0.095%. So neglecting the kinetic energy, we calculate the total energy with a very small error. So that is about this problem. Moving on to the next problem, we have air entering an adiabatic nozzle steadily at 300 kilopascal, 200 degrees Celsius and 30 meter per second, and it leaves at 100 kilopascal and 180 meter per second. The inlet area of the nozzle is 80 centimeter square. Determine the mass flow rate through the nozzle, the exit temperature of the air, and the exit area of the nozzle. So at inlet we have been given all the conditions, and at the exit we are given only the pressure and the velocity. So to calculate the mass flow rate through the nozzle, we have m dot there is some problem with the So yeah, we have m dot is equal to rho AV. For rho it's not given, but all the conditions are given, so we can calculate rho as P by RT. So we can calculate rho at 1, velocity at all conditions at 1. So rho pressure at 1 or the inlet is 300 kilopascal, which is 300 into 10 power 3 pascals, and we have R as 287 for air, and the temperature is given as 200 degrees Celsius, which is 473 Kelvin. So the rho can be calculated. This is 2.21 kg per meter cube. So now we can calculate the m dot. M dot is rho AV. Rho is 2.21 into area is 80 centimeter square, so it is 80 into 10 power minus 4 meter square, and velocity we have 30. So this is 0.5304 kg per second. So this is about the first part of the problem, and to calculate the second part, which is the exit temperature, we can write the energy equation. So for the energy equation for this nozzle at steady state, we will have only change in enthalpy and change in kinetic energy. So enthalpy at state 1 plus kinetic energy expressed as v square by 2, v1 square by 2 should be equal to the enthalpy plus kinetic energy at the outlet. So this h is again Cp into T. Velocity at both the ends are given, so we can calculate this. So h1 is Cp at into T1, which is 1005 into T1 is 473 plus v1 square, which is 30 square by 2 plus equal to Cp is known, which is 1005 into temperature T2 is unknown plus V2 square, which is 180 square by 2. So with this we can calculate T2, which is 1005 into 1005 into 473 plus 30 square by 2 minus 180 square by 2 the whole by 1005. So T2 can be calculated. So this is 457.33 Kelvin. So in degrees Celsius it is 184.33 degrees Celsius. So this is about the exit temperature of the air. Now the exit area of the nozzle can be has to be calculated. So again we can use the same relation, m dot equal to rho AV. Rho has to be calculated at exit condition. So rho 2 is P2 by RT2. P2 is 100 kilopascal, 100 into 10 power 3 pascals. R is 287 into temperature at exit is 457.33. So rho 2 can be calculated. Which is 0.762 kg per meter cube. So now writing the m dot equation for the second or the exit state. M dot is rho 2 A2 V2. Here rho 2 is just calculated as 0.762. A2 is what we need to calculate, and V2 is given as 180 meter per second. And m dot is known earlier, which is 0.5304. So A2 can be calculated as 0.5304 divided by 0.762 into 180. So which is 3.867 into 10 power minus 3 meter square. So this can be written as 38.67 into 10 power minus 4 meter square, or 38.67 centimeter square. This is about the second problem. In the next problem, we have air flowing steadily at a rate of 0.5 kilogram per second to a compressor, entering at 7 meter per second velocity and 100 kilopascal pressure and 0.95 meter cube per kg of specific volume, and it leaves the compressor at 5 meter per second, 700 kilopascal and specific volume of 0.19 meter cube per kg. The internal energy of air leaving is 90 kilojoules per kg, greater than that of air entering. The cooling water in the compressor jacket absorbs heat from the air at a rate of 58 kilowatt. Compute the rate of shaft work input to the air in kilowatt, and then find the ratio of the inlet pipe diameter to the outlet pipe diameter. So I am writing the I will just draw a schematic of this problem. For the problem, this is a compressor. So I will repeat the problem. Air flows steadily at a rate of 0.5 kg per second to a compressor. So drawing a compressor. So the m dot is given as 0.5 kg per second. So inlet velocity is 7 meter per second, and inlet pressure is 100 kilopascal. Specific volume is 0.95 meter cube per kg, and while leaving, it leaves at 5 meter per second, 700 kilopascal pressure, and specific volume is 0.19 meter cube per kg. So some shaft work is given into the system, and heat is transferred out of the system. So this heat transfer out of the system is 58 kilowatt as given here. Now we need to compute the shaft work in kilowatt, and then the ratio of the inlet pipe diameter to the outlet pipe diameter. So calculating the pipe diameters ratio is easy. So I would start with that. M dot is given as rho AV. Since it is a steady flow, we can say that m dot 1 is equal to m dot 2. So m dot 2 is m dot 1. So here instead of rho, a specific volume is given. So I can write this as AB into divided by specific volume. So this A1 V1 divided by specific volume 1 should be equal to A2 V2 by specific volume 2. Now area is given by pi by 4 d square. So I can write A1 as pi by 4 D1 square. V1 is given as 7. Sorry, V1 is V1 is 7, and specific volume at state 1 is 0.95. This is equal to pi by 4 D2 square for the area 2, and V2 is 5 meter per second, divided by specific volume is 0.19. So this will give D1 by D2, which is equal to, I can cancel the pi by 4 values. D1 by D2 is equal to 5 by 0.19 into 0.95 divided by 7, the whole root. So this is 1.89. So the ratio of the diameters is known now. Now we can calculate the shaft work that is done. So from the steady state energy equation, flow energy equation, we have W dot is equal to Q dot plus minus M dot into U2 minus U1 plus P2 V2 minus P1 V1 plus V2 square minus V1 square by 2. So this is the enthalpy term, and this is the kinetic energy term. So now because P and V are known to us, and similarly internal energy change is also given. Internal energy change is given here, which is 90 kilojoule per kg. Now M dot is also known. I think then we can directly calculate. So Q dot is 58 kilowatt. I would write it as 58 into 10 power 3 joules per second, minus M dot is 0.5. U2 minus U1 is 90, because the internal energy leaving is greater than that of the air entering. So U2 is higher, so U2 minus U1 is positive 90 kilojoules. So I would write it as 90 into 10 power 3 plus P2 V2. So P2 is 700 kilopascal, 700 into 10 power 3. V2 is given as 0.19. This minus I have P1 V1. P1 is 100 kilopascals, 100 into 10 power 3 into V1, which is 0.95. Then I have the change in kinetic energy. So that is V2 square minus V1 square. V2 is 5 square minus V1 is 7 meter per second. So solve in steps. So 90 into 10 power 3, multiplying 700 into 10 power 3 into 0.19, I have 133 into 10 power 3. Then 100 into 0.95, I will have 95 into 10 power 3 plus 25 minus 49 divided by 2. This comes out to be minus 5994 joules per second. So the work is done to the system, so that's why we are getting it as negative. So this is 5.9, or I would write it as 6 kilowatt. Okay. Do you have any questions in the problem? Okay, I think this Q should be written as minus 58. So this would be so this is 122 into 10 power 3 joules per second, or minus 122 kilowatt. So since we assume heat transfer into the system as positive and heat transfer out of the system as negative, so this 58 kilowatt of heat transfer should be taken as negative, and similarly work done to the system is negative and work done by the system to the external surrounding is positive. So that's why for the compressor we are getting a negative work. If you have any questions, I can answer now, or I can move on to the next problem. Mr. Ravindra Kumar, can you follow the problems? Okay. Next, I have few problems to solve using the concepts of second law of thermodynamics. So this will mainly involve heat engines, heat pumps, and refrigeration systems. So I thought I would just introduce these three machines. So generally, a heat engine is something that converts heat energy to mechanical energy. So heat flows from a high temperature reservoir. So here it is T1 at a temperature T1, and it produces some work output W, and then in this process, as per thermodynamics second law, it should reject some heat to another reservoir T2. Another reservoir, here it is at a temperature of T2. So I assume this heat transfer from high temperature reservoir as Q1, and heat transfer into the low temperature reservoir as Q2. Now I can write the energy balance equation for the heat engine. So we know from we know from the first law that Q is equal to delta U plus W. So since this process, this heat engine, assume the heat engine operates steadily, there is no change in internal energy. So Q1 minus Q2 is equal to W. So this is a relation concerning the heat engine. Here the temperature 1 is greater than T2, and that is how we get the flow of energy from T1 to T2. So similarly there can be yeah, so here T2 can be atmospheric condition, and this can be some furnace at high temperature, furnace or boiler at a higher temperature, something like 1000 degrees Celsius or something. So this would be at atmosphere, it will be like 20 degrees Celsius or 30 degrees Celsius. And yeah, so now we have something called efficiency. So efficiency is generally defined as output. Okay. I can see that audio is low. I will try to change the audio source. Please let me know if it is better later. Hello, can you let me know if the audio is better now? Still the same problem, so I would try to change to something else. So can you again check? Earlier it was. Oh. I didn't change any option, so can you try to increase your volume or something in your device? Okay, I will try to be more louder. Is it fine now? Can you try to get out of the call and join again? Okay, please try to rejoin the call. Okay, so if your currently your network is not fine, this will be anyway uploaded in the YouTube and the link will be shared with you, so you can also watch it later. And if you have questions, you can ask in the discussion forum there. Okay, coming back, we define efficiency as output by input. So for this heat engine, our desired output is the work done, which is represented by W, and the input given to this heat engine is Q1. So generally the reservoir at low temperature T2 is from is an atmosphere, and we spend some energy in the furnace or boiler to get the high temperature and flow the heat to the heat engine. So the input given to the heat engine is Q1. So efficiency is defined as W by Q1, which is W can be written as Q1 minus Q2 by Q2. So this is by Q1. So this is 1 minus Q2 by Q1. Later, assuming there is no irreversibility, and that means the entropy generation is 0, we can say that this is T1 minus T2 by T1. So efficiency can be 1 minus T2 by T1. So this is about the efficiency for the heat engine. For the heat pump, we have the same configuration. For the heat pump, we will pump the heat from a low temperature reservoir to a high temperature reservoir. So this T1 again here is also T1 is greater than T2. And for this pumping, we give some work as input, represented by W. Here we don't say it as efficiency, here we call it coefficient of performance. So again this is desired output by input. So for a heat pump, we supply some work in form of mechanical energy. So this can be provided by an electric motor or something, and the purpose of the heat pump is to supply heat to a higher temperature reservoir. So assuming in cold countries, the room can be room has to be maintained at say 20 degrees Celsius, whereas the atmosphere outside atmosphere is minus 5 degrees Celsius or something. So we put a heat pump so that we can pump this heat from low temperature reservoir to a high temperature reservoir, and then we maintain this room temperature as 20 degrees Celsius. So this is just opposite of refrigeration, which we'll talk next. So here the desired output is Q1, Q2. So desired output is Q1 and input is W. So similarly, for the refrigeration cycle, we have the same configuration as a heat pump. The work is given as input, and Q2 flows from a low temperature reservoir at T2, and Q1 energy flows into the high temperature reservoir maintained at a temperature T1. So here COP is desired output by input again, and desired output is Q2. Our objective is to reduce the temperature of the low temperature reservoir. So this can be a refrigerator or any or an air conditioned room. say it has to be maintained at 20 degrees Celsius, and the outside atmosphere is 30 degrees Celsius, and we put a heat pump, refrigerant, which will transfer heat from the low temperature reservoir to a high temperature reservoir. And in case of heat engine we call it efficiency, and in case of heat pump and refrigerant we call it coefficient of performance. So the coefficient of performance will be always most of the time it will be greater than 1, and theoretically it is much greater than 1. The point of using heat pump is by giving 1 joule of say the mechanical energy, we will be able to supply some say if this is 3 joules, this can be 4 joules. So by supplying only 1 joule of mechanical work, we will be able to supply 4 joules of heat energy to a high temperature reservoir. So if you are using just a heater coil to heat the air conditioned room in a cold country, we will be supplying by supplying 1 joules, we will be able to only provide 1 joule of heat energy. So by using a heat pump, the heat supply to the room is multiplied by the coefficient of performance. So this is again always greater than 1. So now moving on to the problems. The first problem we have as a steam power plant with a power output of 150 megawatt, and it consumes coal at a rate of 60 tons per hour. If the heating value of coal is 30,000 kilojoules per kg, determine the overall efficiency of this plant. So I would draw the schematic. We have an heat engine which is a steam power plant, and the power output is given as 150 megawatt, and some heat is transferred from a high temperature reservoir which is given by a coal, and this coal is given as 60 tons per hour, and the coal heating value is 30 megajoules per kg. So now we can calculate this Q1. Q1 is 60 tons per hour. So this is 60 into 10 power 3 to convert the tons into kg, and to convert the hour to second we have 3600 in the denominator, and multiplying this with the calorific value we have into 30, and this will give this is 500 megawatts. So we had megajoule per kg here, and this is ton per hour we have converted to kg per second. So finally we have a megajoules per second, which is megawatt. So Q1 is 500 megawatt. To calculate the efficiency, we have the desired output by input. Desired output here is power that is generated, which is 150 megawatt, and input given is in terms of Q1, which is 500, and we have so this is 0.3, which is 30%. So the efficiency of the steam power plant is 30%. In the next problem, we have an automobile engine which consumes fuel at a rate of 28 liter per hour and delivers 60 kilowatt of power to the wheels. If the fuel has a heating value of 44,000 kilojoules per kg and a density of 0.8 gram per centimeter square, determine the efficiency of this engine. So again, this is the same like heat engine we had for the steam power plant. Now Q1 can be calculated as m dot into calorific value. So here m dot is 28 by 60. This is liter per second, and then multiplying with 0.8. So this is gram per cc is also liter per kg per liter. So this is 0.373 kg per second. So Q1 can be calculated as 0.373 kg per second into calorific value, which is 44 into 10 power 3. So this is in kilojoule per kg and this is kg per second. So the output we get will be in terms of kilojoule per second. So this is 16,412. Okay, sorry, this the m dot is given in liter per minute, so this should be 3600. To convert the liter per hour to liter per second, I should divide it by 3600. So this will become so this is 6.22 into 10 power minus 3 kilogram per second. So this is 273.68 kilojoules per second. So this is 273.7 kilowatt. So now to calculate the efficiency, we have W by Q1. W is given as 60 kilowatt, and Q1 we have 273.7. So this will be 0.2192, which is 21.9%. So moving on to the next problem, we have a coal burning steam power plant which produces a net power of 300 megawatt with an overall thermal efficiency of 32%. The actual gravimetric air fuel ratio in the furnace is calculated to be 12 kg air per 12 kg fuel. The heating value of the coal is 28,000 kilojoule per kg. Determine the amount of coal consumed during a 24-hour period and the rate of air flowing through the furnace. So the efficiency is given as 0.32, which is 32%, and W is given as 300 megawatt. Using this, we can calculate the Q1, which is heat energy given to the steam power plant, and AFR is given as 12 kg air to 12 kg fuel, and calorific value is given as 28,000 kilojoule per kg. I would calculate Q1 as eta into W. Eta is 0.32 and W is 300 megawatt. So this will be sorry, it is W by, this is W by eta, which is 300 by 0.32. This is 937.5 megawatt. So this is the heat input. Heat input should be m dot into CV. Now CV is given, and so we can calculate the m dot. So m dot is Q1 divided by calorific value, which is 937.5 into 10 power 3. I will have it as kilojoules per second, and divided by 28,000 kilojoule per kg. So this is 33.48 kg per second. So this is the m dot of the fuel. Now we can amount of coal consumed during a 24-hour period. So to calculate this for 24 hours, we have m dot of fuel, m of fuel is equal to m dot of fuel into time. So m dot of fuel is 33.48. So for a 24-hour period, we have 24 into 3600 seconds. So this is 2.89 into 10 power 6 kilogram. Now we need to calculate the air flowing through the furnace. We know that we know the air fill ratio, which is 12. AFR is m dot A by m dot F, which is 12, and 12 is m dot A by m dot F is 33.48. So m dot A is 12 into 33.48. So this is 401.76 kg per second. I hope the problem is clear. Moving on, we have some problem on heat rejection by a refrigerator. The food compartment of a refrigerator, as shown in the figure, is maintained at 4 degrees Celsius by removing heat from it at a rate of 360 kilojoule per minute. If the required power input to the refrigerator is 2 kilowatt, determine the coefficient of performance of the refrigerator and the rate of heat rejection to the room that houses the refrigerator. So as shown in the schematic, the food compartment is a low temperature reservoir, which is T2, as we have seen in the theory, and the kitchen is a high temperature reservoir at temperature T1, and the heat that is rejected by the refrigerator is given. Okay, the heat removed from the low temperature reservoir is given as 360 kilojoule per minute. So that is Q dot L as given in the figure, which is 360 kilojoule per minute. So to calculate in seconds, I have 360 by 60 kilojoule per second, so which is 6 kilojoules per second. So this is heat that is removed from the low temperature reservoir, and So this is 6 kilowatt. And now we need to calculate the COP. COP is desired output by the input given. Here the desired output is heat that is rejected, which is Q dot L, and input given is in terms of W dot. So Q dot L is 6 and W is 2 kilowatt. So we have COP of 3. And the second part of the problem is to find the rate of heat rejection to the room that houses the refrigerator. So from energy balance equation, we have Q dot L plus W dot. These are the energy flowing into the system, should be equal to the energy going out of the system, which is Q dot H. And we know, so Q dot H is what we need to find, which is QL by plus W. QL is 6 plus W is 2, so this is 8 kilowatt, which is flowing into the kitchen. I hope this problem is clear. Moving on to the next problem. We have a heat pump that is used to meet heating requirements of a house and maintain it at 20 degrees Celsius. On the day when the outdoor air temperature drops to minus 2 degrees Celsius, the house is estimated to lose heat at a rate of 80,000 kilojoule per hour. If the heat pump under these conditions has a COP of 2.5, determine the power consumed by the heat pump and the rate at which the heat is absorbed from the cold outdoor air. So this heat pump is given and the COP is given to be 0.25. We know the temperature at the outdoor and the temperature of the house, and we want to calculate the power consumed by the heat pump and the heat at which the rate at which heat is absorbed from the cold air. So now COP for a heat pump is defined as desired output by input. Here the desired output is Q dot H and input is W. So this is 2.5, which means I can calculate W as Q dot H divided by 2.5, which is COP. So Q dot H is 80,000 kilojoule per hour. So the heat lost by the house is 80,000 kilojoule per hour. To maintain the house at the same temperature, we need to supply 80,000 kilojoule per hour. So that means Q dot H is also 80,000 kilojoule per hour. So this is 80,000 divided by 2.5, which is 32,000 kilojoule per hour. Now we need to calculate the Q dot L. This plus W dot should be equal to Q dot H. So Q dot L is equal to Q dot H minus W. Q dot H is 80,000 minus 32,000 is W. So we have 48,000 kilojoule per hour. So I had few more problems. We can continue it in the next next session on next week. This video will be uploaded in YouTube, and the link will be sent to you by through NPTEL portal, and this notes will also be available in Google Drive, and the same link will be shared with you. Thank you.